Okay, thank you. So very happy to have the opportunity to present our recent work here. So the topic I will cover today is on some application of the thermal tensor networks to the studies of quantum magnetism. So typically, when we are given with a quantum spin model, so we call the tensor network algorithms or methods to solve the forward problem and compute the thermodynamic properties. However, in the study of quantum magnetism, usually we also face with the inverse problem. If you want to know the property or the intrinsic structures of the magnets in terms of magnetic interactions, we need to infer the lattice model from the thermal data. And how to do that? This is the topic I'd like to talk about today. Sorry. So we find a solution with a accurate thermal tensor network method in both 1D and 2D, and with the help from the machine learning techniques to help us to find the spin model from thermal data. The work was done with my students, Sizhuo and Yuan and Bingbing, and we have already posted work on the archive, and the source code is also open on the GitHub link. So we know that the field of frustrated quantum magnetism is moving very fast. So experimentalists are synthesizing some very intriguing quantum material called quantum spin liquid candidates. Here I just listed only a few, some prominent ones. The kidnap materials, here I show alpha lucent chloride. Although it orders below 7 Kelvin, people still find some signature of spin fractionalization, or we say spin excitation fractionalization in such systems. So people believe that this compound is close in proximity to quantum spin liquids. And the Takehome magnets, right? People believe it is closely related to the Takehome-Heisenberg antiferromagnet model. And the triangular-lattice magnets, here I show the ytterbium magnet and gallium oxide. So it has a broad spin excitation continuum. Although there are side mixing between the magnet and the gallium compound elements, so there's still some debate on the nature of the compound. But recently, there are some progress that people synthesized a family of frustrated triangular lattice magnets. The A stands for alkali ions, and Re is the rare earth element. CH could be oxygen, sulfate, or stellium. So, and it is free of side mixing and very promising to find maybe quantum spin liquids. So, however, for each of these compounds, there are a lot of debates still. So, up to date, there's no solid evidence that we have found quantum spin liquids in these realistic compounds. One reason is because these compounds are complicated. The other is that we still didn't fully decode the DNA of these quantum magnets that is spin Hamiltonian and precise interaction parameters. So only with them, we can perform many of the calculations like tensor network simulations and make sure the nature of the quantum states in these compounds. So the question is how to do that. So can we actually infer the manipulated model from experimental data? So roughly speaking, there are two classes of data available in the quantum magnet studies. One is the dynamical measurements, like elastic neutron scattering, μSR, NMR, etc. For example, the INS, to obtain INS data, typically you need to perform measurements on this kind of big facilities, right? So, and you need to apply for mean time. So that means it usually takes a long time. And moreover, the dynamic data are actually difficult to compute, also from the manipulative calculation perspective. Another important kind of data are thermal data, like there's ordinary measurements like specific heats, magnetic stability, magnesium curve, etc., etc. And this kind of data can be relatively easy to obtain, right? So it can be measured on the PPMS, MPMS, so standard equipment in modernized physics departments. So if we can make the most of the thermal data, can we actually determine the pinpoint spin model of the intriguing fluctuating quantum magnets, this quantum spin liquid candidates? Is that possible? So, so I would like here. We would like to propose that this can be done. Okay, this task can be done. So the tool we have actually in the forward process is thermal tensor networks. In 1D, we have actually multiple tools. In 2D, we have also recently developed a method called exponential tensor renormalizing group that can do rather well the forward problem. And for the inverse problem, we need some smart optimizers, and we learned from some machine learning techniques and find some solution for it. Okay, so to be concrete, I firstly introduce some thermal tensor network methods, right? Calculations. The first algorithm I would like to mention is the linearized tensor renormalization group, LTRG. The L stands for linear. So for one-dimensional system, 1D quantum spin chain, for example, its partition function can be written as a 1 plus 1D thermal tensor network. At each site, there's a local tensor, which stores the Boltzmann constants, Boltzmann weights, sorry. And then if we contract along the horizontal direction, the imaginary time direction, linearly, we arrive at a major product operator representation of the density matrix at a given temperature. With this method, we are able to compute directly the thermodynamic properties directly in the thermodynamic limits. It can compute the critical spin chain, right? Like the specific heat to a very low temperature and see the linearity behavior. It can also be applied to some 2D model. Here I show, this is a 2011 paper actually, so applied to solve the honeycomb lattice Heisenberg anti-Feynman model. Okay. However, for more challenging 2D models, we need to develop a more capable technique. So this is called exponential tensor renormalization group method. Different from LTRG is the finite size algorithm. So we map the 2D system into the snake-like parse and represent the density matrix with this snake parse NPO. Okay, so that means we can only compute systems with a finite width, but not infinite system size. Regarding the length, you can go to rather long, less restricted. After obtaining a row of beta, that means density matrix at some temperature, we keep squaring it and cool down the system exponentially along the temperature axis. So it can reach low temperature very fast. Okay, so now I show that what kind of problem can be solved with XTRG. For the 2D quantized model, which is a very fundamental model in quantum magnetism, it has a thermal phase transition at finite temperature, right? So for this kind of system, we can compute a system size like width 9 and length 18, so it's more than 115 sats. For the superlattice Heisenberg model, another important model, so we can compute the YC8 cylinder. Here the length is being extrapolated to infinite. So with this calculation, we can even, because these calculations are performed at a rather low temperature, so we can even try to estimate obtain a rather accurate estimate of the ground state energy and the spontaneous magnetization of this model. Okay, so beyond this models without a sign problem in quantum Monte Carlo, we can also use this XTRG to study some challenging ones that is otherwise very difficult to simulate. Right? For example, the triangular-lattice Heisenberg model, antiferromagnet, of course. So with this, we established two temperature scales of this frustrated antiferromagnet. Only below this low temperature that previously inaccessible, the system entered the renormalized classical region. And between the higher temperature scale and the lower temperature scale, there's anomalous liquid-like state. And with 2D Fermi-Hubbard model, so we can also compute system size up to with 8, right? And we can compare to ultra-cold fermion quantum simulations. Okay, so with XTRG in 2D, with LTRG in 1D and XTRG in 2D, we are confident that we can actually try to fit the experimental measurements, the experimental thermal data, and to try to hand-tune, in a hand-tuned manner, to find the microscopic spin model of this quantum magnets, right? However, it is still very tedious, laborious, right? So these are the process that we tried to fit the thermal data of cerium, magnesium, gallium oxide, and the lucent trichloride. So to make this process more efficiently, we need a smart parameter optimizer. So now I introduce the optimizer we use, we find useful in our study. So this is the whole procedure now. We have a model, right? We start from some model with some parameters, and we give this to the thermodynamic solver. It could be a thermal tensor network method approach, right? Then we compute the thermodynamic quantities, these curves, and compare it to the experimental data, from which we can compute the fitting loss, right? And then we let the optimizer to determine which is the next model we should try. Okay. The most naive optimizer is the random grid search, right? So we just throw the dice and choose the next parameter point to compute. A better optimizer is the autogradient. It's a gradient-based optimization. If we know the gradient of the loss versus the Hamiltonian parameter, we know how to decrease the loss. Right? So then we can go one step further and do this loop iteration, go one more iteration until it converges to the optimal parameter point. And we can also have a gradient-free, non-gradient search method called Bayesian optimization, which I will introduce later in a minute. So this whole process should be automatic and efficient. So you do not need to do a hand-tuned search, can save some label, and it's systematic, right? So you can explore a large parameter space and reduce human bias to make sure that we are not fitting the Fermi's elephant, right? But are truly looking at the optimal parameter point in a reasonably large parameter space. Okay. So, okay, to be concrete, the automatic gradient. So recently, thanks to recent work, we make our tensor network algorithms, tensor renormalization group procedure, fully differentiable. So we need to design a forward process from the parameters. This is consists of a computational graph. So from the coupling parameters, we construct the Hamiltonian H, usually in the MPO form, matrix operator form. And then we compute the partition function, some quantities, and all the way to the fitting loss. In the backward process, following the chain rule, we can actually compute the gradient, right? The partial loss, partial L, partial Hamiltonian parameters. So we know once we compute this gradient, we can use it to optimize the parameter, to minimize the loss, right? The second method, which I actually recommend more, is the Bayesian optimization. So once the fitting loss is well defined, right? Usually we define it as the square of the distance. Then we design a Gaussian process. That means for each parameter point, we suppose they follow a joint multivariant Gaussian distribution. Okay. So as shown here, so in the course of Bayesian optimization, this joint Gaussian distribution will approach the true distribution as protein as shown in the figure. So all these are measured points. So it has no uncertainty, right? Because it has been measured. The other points we have estimates, right? This the like curve, and it has some uncertainty, the sigma n. So, as you make more and more measurements, the distribution will be converged to the true one we have typically. So it's just like you are doing some gold mining. So you know there's some gold, some well, but you don't know exactly where it is. So you have to dig some hole and make some measurements. And from the information there, you figure out roughly where the gold could be distributed, and then make more, dig more holes, and eventually find it. So it's like this process. And once this Gaussian process has been converged, or in the course of converging your Gaussian process, you call the acquisition function to make a choice. So which Hamiltonian parameter or parameter point should be measured in the next iteration. So usually we use EI. So in the current study, it could be either PI or LCB. There are some choices. So EI actually minimize the expectation value of the loss. Okay, so with this kind of optimizer, I just show you some animation to give you some flavor, intuition that how they work. On the left is, sorry, should work, right? Yeah, okay, good, eventually. So in the gradient-based optimization, see, in this artificial landscape, there are actually one global minimum and two local minimum. So yes, the gradient-based method can find this global minimum, but it has also a good chance to betrayed the local minimum. On the right hand is the Bayesian optimization. You make measurements, like you put these parameter points in your simultaneous level calculation, and at the same time, when you do more and more measurements, you have a more clearer and clearer estimate of the landscape. See, after Bayesian optimization, you actually figure out there are just three minimum, one global and two local minimum. Yeah. So maybe we can go one step, we can compare them side by side. Okay. So both methods are actually quite efficient, and you can find the global minimum in a reasonable number of iterations. Okay. Because our manual calculations are time consuming, are very expensive relatively. So we would like to call our simultaneous network, our manual solver, as few times as possible, and then find the global minimum as soon as possible. Okay, now let's give it let's try our method on some artificial experiment data. So we generated some thermal data from some model, right, with a given parameter. The model we consider is the Heisenberg antiferromagnetic chain with x-axis interaction. So there are two parameters, jxy and jz. So we generate the thermal data from LTRG. That's the is a 1D infinite system. So the orange data are the generated data. So to make it, we also add some Gaussian noise to mimic the experimental data. And of course, we can try to call another LTRG, right? Combined with autogradient method or Bayesian optimization to find the parameter. But we want to make this game some more difficult, or more challenging, right? So we want to fit the thermal data and find these two parameters with just a high temperature solver, AED solver. So tenside ED, for example. So with the ED simulator, a solver, you cannot fit the whole, fit the temperature, fit the thermodynamic curve in the whole temperature range. You can just cover a finite temperature window, right? Because the ED solver suffers from finite size effect. Here we see that the blue curve, the ED's data, deviates from the infinite chain data at low temperature. However, we can set the Tcard, right? Here we set the Tcard around the peak of the specific heat to see that only the data points above the Tcard are included in the fitting. Right? We would like to see, can we retrieve the two parameters, the JXY and JZ? The answer is yes. So in these two plots, we show the landscape. The landscape are actually scanned. Okay, it's a scanned landscape with ED solver. So we can see that there's only one a global bright point, which rightly located at the ground truth. The parameter points, the parameters are used to generate the thermal data. So that means it can be found. And then let's check the efficiency of the three optimizer. The random grid search, you can use this method to really find the optimal point. That's the original parameter point. So after more than 500 iterations, with autogradient, this number can be reduced by 10, so like 15 times, 15 iterations. With Bayesian optimization, this can be we can locate the optimal point slightly above 20 iterations. So it's highly efficient. Okay, so in this box plot, we deploy 100 independent workers, and the Bayesian optimization has the overall best performance. You can see here, after certain iterations, the 100 workers all reach destination. Okay, they reach the same destination, the optimal point. And the autogradients, although it also the performance is also good, but it has the deficiency that it could be trapped in local minimum, and the grid search compared with the two Bayesian autogradient method is less efficient. Okay, fine. One can still ask a question. So how to choose the Tcard, because you have a finite size solver and you want to fit the data and the thermodynamic limits, right? Then how to choose a Tcard? If the Tcard is too high, can you still get meaningful information about the interaction parameters of the Hamiltonian? The answer is like this. So we perform some calculations. We set the Tcard from high all the way to low temperature, right? So when the temperature is very high, like A, the dashed line A here, we can still get some interesting information. We will see a ring-like bright region. Right? So that means we indeed has lose some resolution. Right? We do not exactly know what the JXY is, what the JZ is, but we know the square sum. So we know the strength of the interaction. So when the Tcard decreases, we'll see something like symmetry breaking along the circle. Right? We'll see that when the temperature is low enough, you will always have two bright points. Okay, so one is the original, the ground truth, right? I mean, the parameter we use to generate data. The other is a symmetric points with the same JZ value, but the JXY of opposite sign. This can be understood, and this should be expected actually, because they have exactly the same spectrum. And in the thermal data you provided, to fit the specific heats and the longitudinal stability cannot actually distinguish the two. So, moreover, when we locate these 2 points and we decrease the temperature further, we find that the fitting is robust, right? The landscape is not scooped. But even though your ED calculators cannot really give you a reliable thermodynamic limit data at so low temperature, it's still the fitting is still robust. That's good. Okay, so if we still would like to break this degeneracy, we're not happy with this twofold degeneracy, we can add more data. Okay, so if we add the transverse susceptibility here, as shown here, this chi xy, so we remove this degeneracy. And we see now there's only one bright point, which rightly located at the original parameter point. Yeah. So and with this, we retrieve the true parameter jxy equals 1 is found. Okay, so let's with this test, let's jump into realistic materials. The first realistic materials.
You still have 5 minutes before the questions.
Okay.
Yeah.
So the first compound that we consider is copper nitrate. So which is a spin 1 chain. Okay, we start with spin 1 chain. It has a strong, weak bond, so it's an alternative chain. So it has parameters J and alpha, and of course some lambda factor. So previously, people fit some of the measurements and determined some parameters. Okay, so we see that the J is like around 5 Kelvin, the alpha is 0.27, 0.23. So how about our automatic parameter searching? In this plot, we show our results. We fit this specific heat under variance magnetic field. And our ED solver on Tensor again can already give us surprisingly good result. We find that J, the coupling J is 5 Kelvin. That's actually quite accurate. The alpha, on the other hand, has very wide, has larger uncertainty, right? But it's still reasonably good. For 2, if we use LTRG, using a infinite chain solver, and then we see that the uncertainty alpha is significantly reduced. And the previously hand-tuned, fitting, right? The result, this triangle is actually very close to the global optimal point. So with this, we reproduce the microscopic model for the copper nitrate. And as a byproduct, we introduce some anisotropy in the system, see the indeed goes to 1. So that means there's no SSZ anisotropy in this compound. This has never been really tested seriously. And with our method, we can see this very easily. Okay, for 2D, the 2D materials are more challenging. And this is the triangular-lattice cerium magnetic gallium oxide. So this is a triangular transverse field Ising model. These are the thermal data from different groups. We plot them together and find the agreeing with each other rather good. And with the fitting, we can actually decode its Hamiltonian like this with the parameter here. And this model, this magnetic quantum spin model actually has a very interesting phase diagram. It has 2 BKT transition and a floating KT phase in between. So we actually also work closely with experimentalists and find some dynamical evidence of the existence of the KT phase. Okay, so this is the background on the TMGO compound. So now let's use our automatic parameter search method to see if we can confirm this fitting, this hand-tuned fitting. Okay, so again, we use 3 times 3 ED first, and then use a much larger system size, LXTRG on YC 6 times 9. So these are the results. So with ED, the Tcard cannot go to very low because it's really small system size. But we can see that actually we can already reasonably good locate the J. The J should be around 10 Kelvin. Of course, the delta, you can see delta and the J2 has very large uncertainty because you cannot, the Tcard is so high, right? So you have not so good resolution. But when you use the XTRG and the Tcard goes to much lower temperature, the resolution is improved. And the hand-tuned parameter is again agreeing very well with our automatic searching. And the spin wave fitting, again, is actually out of the most likely region. Okay. I very briefly mention our KTIF material, Lucent chloride result. So we can use XTRG plus Bayesian optimization and get this landscape. And from this black point with a parameter here, so we can actually reproduce the most major experimental features. So and the model is K, J, gamma prime model, and we can make further predictions. And now working closely with experimentalists to check those predictions. Okay, so with this method, we think we can the tensor network methods, with the help from some smart optimizer, from machine learning techniques, can indeed help us to study these fluctuating magnets. So we know this. I mentioned earlier that this family of magnets, it has like 15, 16 members, right? They all have a similar Hamiltonian, but different parameters. People have some knowledge on which parameter region can give you quantum liquids. The next question is, which compound actually has the interaction parameters most close to those quantum spin liquid region. So this is some job that our method can do some help. Okay. And our code and this package we call it QMagen, so quantum magnetism genome. So it's now open source. So we can check on the GitHub, and also some details of our archive paper. Okay, here's the summary. So the tensor network solver, so my tensor networks plus some efficient optimizer, can be used to solve the inverse manipulative problem. The take-home message is that although to decode the microscopic spin Hamiltonian at first glance a problem intractable, right? Because the forward problem is already very challenging. But the key point is that you do not really need to solve the full manipulative problem. If you can only solve a finite size down to high or intermediate temperature, you can already make the most of this tensor network calculation to already give you a very good estimate of the interaction parameters in the compound. So we think the QMagen would be a helpful in the search for quantum spin liquids. With this, I would like to thank you for your attention.